Hi, welcome to this week of our Watch Me Work series at Cockroach, where we take a glimpse into the work that engineers here on the team do, and try to demonstrate some of the challenges that we face while addressing changes in the code and changes, as we try to improve CockroachDB. And so I guess Dan named this one Transaction School, which is kind of a neat name. What we're going to be doing here today is looking at schema changes over a new form of a table that we added within CockroachDB to support multi-region deployments. And we're going to look into speeding these schema changes up. Specifically, schema changes that are adding or removing columns from these tables. We noticed that they are slower than they need to be, and so we're going to look into how we can speed them up. And so the title here, discusses this: speeding up schema changes on global tables. And so I'm going to first just jump over. I think people can see this. Jump over to some of our docs that are. We can see these are new docs for 21.1. And what we did in 21.1, which is our upcoming release of CockroachDB, is that we overhauled the abstractions that we expose to users through SQL for multi-region deployments of CockroachDB. So these are deployments within maybe a few nearby regions, or even deployments across the globe with parts of a database spread out across this multi-region topology. And so a user of CockroachDB may want to use this multi-region work for two reasons. The first being that by spreading data across multiple regions, we can survive geographic failures. And so these failures can be at the level of a data center zone or a region zone, all the way up to a failure domain of an entire geographic region. Maybe there's a power outage that affects all zones within a region, or some other type of failure event that occurs like that. And so the ability to survive increasingly large failure, the failure of increasingly large failure domains is one of the main reasons to use multi-region. But the other one is that users of a database may want to provide low latency access to data across geographic regions. And that's mostly what we're going to be talking about today, is a new type of table that Cockroach added. In fact, Cockroach added this split between these two tables, one called regional and one called global. And so we are going to be discussing these global tables in a little bit of detail, and then we're going to be talking about how we can speed up schema changes on these tables. And so I'm going to jump down and just give a brief overview of what these two table types are. We call them table locality settings, and within a multi-region database within Cockroach, every table has a locality setting. This dictates effectively the locality that we are assuming is in effect for the data within this table. And so we have two types of tables. We have a regional table and a global table. And a regional table is used for localized data, so data where we want fast reads and writes from a single region. And so this can be a table that provides for all of its data fast reads and fast writes in a single region, or it can mean on a given kind of on a row by row basis, we provide fast reads and fast writes. And this is packaging up a concept that Cockroach already had called geopartitioning, and packaging it up in a much more a much cleaner abstraction that will be a lot easier for people using SQL to understand. And so the regional tables are they're closely aligned with what Cockroach has already provided. And then on the other side, there are these global tables. And this is a new concept in CockroachDB. These global tables reduce write performance, so they slow down writes, but in exchange, users get fast read access, fast consistent read access across all regions in their database. And so they're optimized for low latency reads from all regions. And so, yeah, as the doctor's saying, they're optimized for low latency reads, and the trade-off is that they'll incur higher write latencies. And there's some complex clock manipulation that we have to do under the hood to get these to provide this guarantee. And part of this is drawing from systems like Spanner. We're drawing inspiration from a system like Spanner, which has this notion of a commit wait phase. So when we write to a table, we end up waiting before acknowledging that write to make sure that every potential follow-on read will observe the write that we just performed. And so we call this a commit wait state. It's this delay that we impose purposefully at the end of a write to one of these global tables in order to ensure linearizability or read your writes, as it's known, on any follow-up reads. And so this all works, and it provides the consistency guarantees that we'd like. But what we've noticed is that, and this is what we're going to solve in this session. What we've noticed is that it imposes more of a delay on schema changes than strictly necessary. And so we've seen that in cases where a schema change is adding, kind of backfilling the rows during an add column operation or a drop column operation, it ends up paying this commit wait state on every chunk that it's backfilling. So you can imagine if we have a 10,000 or a 10 million row table, and we are backfilling chunks of 10,000 rows at a time, we end up paying this commit wait state 1,000 times when we really don't need to. We do want to have some notion of consistency on the entire schema change operation. So we would expect if I do a schema change and I add a new column and I immediately read from that table, I will see that column in existence after the schema change is completed. But we don't need to pay this wait on every single chunk of the schema change. We just need to do it once. And so we're currently paying this cost. In the ask here is to go back and restructure part of our transaction API to avoid the wait when it's not needed. And so, yeah, this issue discusses it fairly well, where each chunk is currently performing this commit wait stage of, it's currently 800 milliseconds. In the future, this commit wait will be a lot less as we push on actually improving our clock synchronization. But for now, yeah, we're waiting 800 milliseconds on every chunk of this schema change. And so to demonstrate why this is so bad, we actually had a test that caught this. It's kind of interesting to see what this test is doing. So this test was performing a number of different schema changes and actually trying to get into error states and making sure that we handle those error states correctly. So it was canceling a column addition. It was canceling during a primary key swap. It was doing a lot of nice things. And what we noticed is if we didn't overwrite or override in this test, the commit wait duration, then we noticed that make this verbose. So this was actually a comment we added in later. Drop the close timestamp target lead for global tables because it made this test go from 2.5 seconds in duration, and made this test go from 2.5 seconds in duration up to 35 seconds. So it got extremely slow because we were paying this commit wait penalty on every single operation. And so we can remove this when that issue is addressed. So what I'm demonstrating now is just how bad things are without this tweak. So I think even right here, we're going to see it. This is a subtest that is performing, it is creating a global table, and it's altering, well, we might not see it on this test. Let's see. We can see this test is quite slow right now because we disabled this override, and so I guess we probably are paying this penalty then. Yeah, so I guess these are slowly completing, but we can see just how slow this is, right? And so let's try to, we're up to 89 seconds. Let's add this back in. For now. See how much faster it is. We were at 89 seconds before, and we weren't even partway through the test. So let's see how much faster this test is when we disable this commit wait operation. Yeah, so we see that it's going right along. It's a lot faster now. And so I think we want to narrow in on one of these subtests, and we can use that going forward as a good litmus test to see if we are actually making improvements as we go. Let me do this test. So I'm going to cancel this, and let's just time just this one subtest. And so what we're going to do is, ideally, we'll be able to demonstrate how much slower things are with this commit wait state. And then we will go in and actually disable it in a certain place in the code during this index backfill operation. We'll disable it. We'll actually kind of collect this this delay that we need to pay, and we will try to only pay it once for the entire operation instead of paying it on each chunk. So now we let's see how slow this gets. I think this is probably what we were referring to by 35 seconds. So that took 2.1 seconds, this subtest right here. We see that there. This is already taking a lot longer. We just let that run. And let's dive into the code a little bit and find where this column backfill is. So is that completed? No, it's still not completed yet. So I think what we're going to do is, let's see where, this column backfiller object that it's a processor for backfilling columns. And so it's used for add column, I believe drop column. These are various forms of schema changes that have to rewrite an entire table and augment the values that are written in that table. And so it currently does this using standard CockroachDB transactions under the hood. And it does so with some chunk size. So it will go maybe, I think the chunk size is 10,000 rows. It will go 10,000 rows at a time, and it will rewrite those rows. So let's let's see if we see if we can try to understand this a little better before we actually go in and start making changes. Is this finished? So we did see, without commit waiting, 2 seconds. With it, 70 seconds. So that is, I guess, a 35 times slowdown, 35x slowdown. We want to avoid that. This is still running. Okay, so run column backfill chunk. So what does this do? It takes a transaction. So we have a key value transaction. And it has a chunk size, a table descriptor, and then a span. And so what this is going to do is it's going to use this transaction to modify the rows within this span. So a span is a key start and a key end. It's a range of keys. And it's going to, I guess, read those rows. So read those keys. The next set of rows. Looks like it's adding on some of these rows. So iv.calls. So it does some manipulation, and then it updates these rows using, I guess we had a batch here. So we're using a single batch, batching these all up in a single operation. We have a row updater. So this is actually the exact same, where is that row updater? This is the same mechanism that, here we go. The same mechanism that actually is used for update statements. And so we're effectively just running an update statement behind the scenes on chunks of 10,000 rows or whatever we have here. And then we issue this batch, right? So txn run or commit in batch, also commit. Okay, so this is, we actually run also commit? Yes, we are. That's fantastic. Okay. So we are also committing this transaction. And so, very good. What we want to do is we want to disable the commit wait operation on each chunk. We'll likely buffer up in this column backfiller some state on the largest transaction commit timestamp. maybe let's X commit exam. And then I think in flush, it's matching some backfill. Fish buffered work. Perfect. Okay. So when flushing, we will we'll actually wait out this max commit timestamp. And so I don't know how long we'll go before flushing. What do we call this? We seem to, yeah, we'll just go through all the spans one by one, just running these chunks. Chunk size. And then we'll flush. Okay, this will work well then. So what we want to do is down when we're actually flushing this, we'll say to do. Let's go please. So we're going to need to augment this KV transaction object with an ability to disable commit waiting. And we have some questions about how to do that, because we want to make sure that if a user of this API is assuming responsibility for commit waiting, then we want to make sure they actually do it. So let's see. So that's how it works, please. So this TXN object is the interface. It's kind of right at the boundary between Cockroach's SQL layer and Cockroach's key value layer. And so this allows SQL to interact with Cockroach's key value layer through serializable transactions. And so everything the SQL layer is doing, whether that be writes or reads, it all kind of flows through this transaction object. Let's just start out by adding down here. So we say is disable. I don't know if that's not really disabling. We want to make sure it's clear to callers that they aren't allowed to skip this operation. They just need to promise that they are going to do it. So disable may be the wrong word. We may want to call this something like defer or In fact, it may be best not to even return a timestamp here, and instead to return some handle to this commit wait operation, so that we don't even leak this state any higher. We don't force the callers of this to have to understand how to even perform a commit wait. We just return some handle to do so. So for instance, we could just return that. Let's just call this deferred. All right, we can bring this up later, but this looks good. And so we're going to do two things here. We are going to first disable the auto commit wait, if you want to call it that, from the perspective of this transaction. And next, we're going to have to implement this executable closure to perform the commit wait operation. And so let's see how some of these other methods are implemented. So we have this sender object. This is not working out too well today. Extent sender. Jeez. For commit wait, let's just pass this straight down. I guess we'll have a similar method or comment here. Work this a little bit. Yeah. So, maybe commit weight here. So first, we're going to want to just pull out. There's some checking in here that I don't want to do. Let's just say. Well, this auto. So what I'm going to do here, I set this commit weight deferred state. So it was deferred, and so now the transaction won't actually perform this. Transaction won't actually perform this commit weight. And then this. And then we can actually go ahead and return this. Well, context. So it would be nice to package whatever closure we're running here up into some method on the transaction object itself, so that we can then say return tc dot maybe like that. What did we just touch here? Okay, so we're taking this transaction interface right here. We have this transaction sender interface, and we are augmenting it with one more method. So we have this defer commit wait method now. And so this, I'm not sure if I actually need the context initially, but it will return this commit wait handle. And so then the caller of this will then later be able to say, okay, I want to commit wait now. Versus having the transaction automatically do this when it immediately after it commits. And this will allow us to effectively coalesce all of these commit wait operations across the chunks in the column backfiller. And so if we do this, the first thing to do is that we're going to need to lock the transaction support sender. And then I think what we want to do is check to make sure that the transaction has committed. If it hasn't committed, then there's nothing to do. Right, there's no commit wait operation. So if it has not committed, we just return. Otherwise, we want to actually run this. And so one of the nice things about this operation, and this comes out of, well, yeah, one of the nice things about this operation is that I believe it's idempotent. So we don't actually have to maintain any state about, that might not actually be true. Yeah, no, it should be idempotent. And the reason why is because if we need to wait until maybe time 15, and then we do this. Maybe it's time 10 now, we need to wait until time 15 for it to be safe to acknowledge this transaction. If we then perform that wait of 5 seconds, or 5 milliseconds or whatever, and then we go back and we call this again, we're going to see, okay, I still need to wait until time 15. But it's already time 15. And so that means that this, we're not going to wait at all. We've already done the wait. And I think that just falls out of this. We shouldn't need to rely on that property, but it is nice to have. And so I think what we need to do is say maybe commit wait false. This is not an auto commit wait. And so because of that, yeah, I think that's all we need. Is that all we need? So this succeeded. All right. So then what we're going to want to do is I'm going to say defer the commit. Yeah. I'm going to say if error equals nil. Slice of these nil. Here, we are going to loop over each of these functions. So for functions, I think we just need to call them, and then I'm supposed to set this to nil. And so the operation, kind of the process of flushing this column backfiller will actually perform all these commit wait operations. And since they're back to back to back, they will compose to the point where the waiting will effectively be coalesced across all of them. So we won't have to perform this wait across each one. And I think we can. Let's test this out. Let's go back to our test. We have this commented out. So we should be, I guess before we saw that this test was taking 90 seconds or something along there. Let's see. 69 seconds. Perfect. What we hope to see here is that we're going to wait a lot less time. It's going to take a lot less time to perform this schema change. And we'll want to confirm that right around this boundary. Maybe we can try disabling and re-enabling that right there. And make sure that actually causes this test to slow down and speed up as we expect. That's a good way to confirm that what we did actually is having the effect that we want it to. This takes some time to compile. So that CPU is pretty hot up there in the top right. Yeah. Chrome. Oh, Chrome. That's interesting. This may be maybe the actual streaming. Yeah, this may be why my compilations are so slow. Streaming on all these different channels. Yeah. So at Cockroach, we have this this concept of we call it a GCE worker. Just these cloud VMs that we oftentimes develop on, similar to how a lot of companies, people have these desktops that they just SSH into and do most of the work on. Would have been a better idea to do that here, to use one of these VMs here, so that there's my laptop being slow isn't affecting this, but this is just easier. All right, well, that did not work. That did not work at all. Why didn't that work? So I guess, are we calling the nil function in our commit wait functions? Okay, that's not good. Why do we have a nil function? Error equals nil. So if error equals nil, we expect this to have completed. And so I know that we are not, yeah, we're not actually calling the sender's defer commit wait. All right, that should be easy to fix. Try that. So we were, the way this transaction object works is it's kind of a shell that is exposing this API that we want to expose to SQL, but it doesn't have very much business logic in it. We actually see that this sender object down here, this txn.mu.sender object, this txn sender interface, that's what implements most of the transaction business logic. And so I guess we had this transaction struct is mainly there to provide a clean API to do some mapping between higher level types and some of the lower level protobufs. And it's also there to manage transaction retries. But what we had been forgetting to do is actually call the kind of pass through this method down to our sender object. So now we expect, and I guess that demonstrated that we were not waiting for the test to run very long. We were just we just had a bug. So once this finishes compiling, I think we'll see this go fairly fast. And if not, that means we have not actually fixed this issue. So yeah, this is the primary way that we do development at Cockroach. Just wait until things stop panicking, and then it's good. So once we get this working, we can talk about the test that we'll want to add here. I think, so what will we want to add? There are a few levels that we want to add testing around here. One is that we'll want to add it right around the transaction coord sender. So kind of our implementation of this commit wait operation. We'll want to mock out, or I guess we'll want to extend the test that is already testing commit wait to incorporate this option that we're exposing to defer the commit wait operation and hand responsibility of that to a caller. And so I guess we will want to make sure that no wait happens when this this function is called or this method is called on the txn coord sender. And then we will want to also assert that the wait does end up happening after the fact once we call this method that's returned. And the way that I guess we can show that test. The way that the test currently works is it uses a mocked out clock so that it can assert that we're actually waiting for the right amount of time. So it let's do the test. So I believe that it's one of these tests where we actually have a combination of 4 different parameters, and so we run each parameter with a true and a false value, and so I guess that's for a total of 16 different subtests. And so it tests that our linearizability mode is enabled, which I guess is poorly named because linearizability is a little poorly defined. Probably should be called strict serializability. This effectively adds a bit more of a weight to ensure that we don't have this, what's it called? This causal reverse anomaly that is discussed actually in the original Jepson report for CockroachDB. This avoids that anomaly by waiting a little bit further. Then we have 3 other parameters. So does the transaction commit or roll back? Is it read only? Does the transaction commit at a future time? And so the test, it spins up a transaction in a Go routine. It waits until the transaction is ready to commit, and it sets up the transaction however the test would like it to, and then it depending on what the transaction is doing, it determines how long it expects it to wait, and it builds up this, accumulates this expected wait duration, and it then slowly increments a manual clock. So this is kind of a mocked out clock for the test. It's incrementing it by a set number of nanoseconds, and it keeps on kind of each time it does that, it says kind of checks if the transaction is done waiting or not. And if it is, then it asserts that this is exactly where I expected it to stop waiting. If it's not, then it complains and says it didn't wait long enough. Let's jump back here, and I think that's what we wanted to see. I think 6 point. It's still a little slower than I thought it would be, but that's not 69 seconds. Right, let's run this one more time now that we're not mixed up with the compilation. All right, 5.14 seconds. So that is a lot better. I think that adds up, because I think what's going to happen is we still need to, since we are no longer using this override, we still have a full 800 millisecond around there wait, but we've now coalesced it across all of these chunks. And so I think that's a good confirmation that what we did worked. What we can do though is this nil, and then we can actually break what we just did. This is often a good way to make sure what you did actually had an effect. We're going to break what we just did, and we expect this to jump back up to 69, 70 seconds, which might actually take us to time. So we'll jump over and discuss a bit more about testing while we let that run. So I think we will either want to extend, for when it comes to testing what we just built, we'll either want to extend this test or write a new one. Not sure what will be easier. I think we can actually extend this test, and we can do so. Yeah, I think we can extend this test. A little old hand down here. use a separate channel in this deferred case. Oh. Not necessarily sure how we want to structure this. I was gonna take responsibility for publishing on this error channel down here, so that the test would all, the assertions it's making actually wouldn't have to change at all. But we can figure that out later. Just want to see. So yeah, so we did see if we aren't deferring the commit wait, then we have to pay it synchronously on each chunk. And so the test got 13 times slower right there, which is a great confirmation that what we're doing checks out. We'll also want to add some testing above this layer to make sure, kind of property testing, to make sure that by deferring the commit wait, we still ensure consistency. So we should still have, we still read our own rights. So anyone who issues this schema change will still observe, they will still observe all of the added columns on the table, even if they query the table immediately after the schema change completes. And so I think I'm going to leave it there because that's a satisfying place to end, where we see with our change, the test takes 5 seconds. Without it, it takes 65 seconds. It confirms that what we did here works, and now there's just a good amount of actually polishing this off and testing. So I appreciate everyone spending the time today, and also I'd encourage everyone to jump over to Large Data Bank, Jordan's stream that's coming up in a few minutes. He's got I think he's going to do some pretty cool things this week, like he always does. So definitely, if you want to continue, jump over to Large Data Bank. With that, I'll say goodbye for the day. So thanks everyone for coming.